Welcome to my channel. I would wish you kindly tap the subscribe button. It is in red. When you tap it, it will turn gray and you'll be subscribed to my channel. Whenever I upload a lesson, you'll be getting direct notifications. Today I'm doing a lesson on physics. And the topic I would like to introduce is a Form 3 topic with the concept, though it's students. The topic is called the quantity of heat. The quantity of heat. I have written it on board. We all know that heat is a form of energy. It is a form of energy that flows from one body to another. It's just a bit of some introduction. Though we know these basic things about heat, it's a form of energy that flows from one body to another due to temperature difference. So when two bodies are having different temperatures, it flows from the hotter one, or the one at a higher temperature, to the one at a lower temperature. When you step a cold floor, you experience some coldness because your blood is having higher temperatures, or your body is having a higher temperature than the floor. Therefore, heat flows from your body to the floor, and that's why you experience a coldness. It is flow of heat from your body to the ground, which is colder. Therefore, if a body is colder than another one, if this is a body at 70 degrees Celsius and another one at 22 degrees Celsius, then heat will be flowing. Heat will be flowing from the hotter one to the cooler one. Therefore, we see now the concept on heat flowing, it translates to heat being lost and the heat being absorbed. Therefore, if it flows from here, body A loses heat while body B is absorbing heat. Now we can say that the loss of heat leads to coldness or decrease in temperature. While absorption, the reception of heat now, of heat, leads to hot, which is increase in temperature. Increase in temperature. Okay, though the way cold and hot, they are very relative terms, because a body can be cold, but relative to another one, it becomes cold. In this case, we are saying that body B, because of 22 degrees Celsius, compared to 70 degrees Celsius in A, B is cold. But now if we compare this one with the highest block at negative 2 degrees Celsius, which has not melted to water yet, this is the highest block, and call it body C. Then now, even though this one was cold, now relative to this one, it becomes a hot body. So, that's basically the concept behind what heat is. The type of energy which flows from a body to another one due to differences in temperature. In other words, here, energy diffuses from where it is highly concentrated in the hotter body. Heat energy is high, Therefore, it flows or diffuses, in other words, to the place or to the body, to the substance where it is lowerly concentrated. I would like to bring to us now a term now, which is maybe new, and we'll call it heat capacity. We'll call it heat capacity. Heat capacity. Heat capacity. We can take this demonstration. When you boil water of a small, when you boil, let's say in a beaker, yeah? Let's say we're boiling here. This is heat. This is 250 cubic centimeters of water. 250 cubic centimeters water. Then another setup where you heat a liter of water. Here now is a bigger setup. You heat a bigger quantity. We can say this is a liter now, or 1,000 cubic centimeters of water. So now, when you heat this and this, there are logical observations which we make here. I know you've been doing these things. You've eaten, you've cooked. So, when you are boiling this water, for it to boil at 100 degrees Celsius, it can take 7 minutes. 7 minutes. But for this one to boil, it can take around 15 minutes. It takes longer to heat a larger volume of water to boiling point. Or else, if you give them equal time, you heat both of them for 7 minutes and this one also for 7 minutes, then you now withdraw the heat and you measure their temperature. You may find when this one is at 90 degrees Celsius, the bigger volume is still at 61 degrees Celsius. 61 degrees Celsius. Therefore, you find that now the larger volume of water requires greater amount of heat to achieve a given temperature. Therefore, if you give the two a common temperature to be reached, and you want this one to achieve 100 degrees and this one 100 degrees, then you will take longer time for the larger volume of water. And take this for your benefit. Now, the greater the volume, the greater the heat energy required for the amount or for the substance to raise the heat it has with a given unit. Therefore, if, for example, you are cooking ugali for a big school like Muka Girls, and another case whereby you are cooking ugali for your nuclear family with 5 people, you discover that now, for you to prepare the ugali for Muka Girls, you spend even an hour preparing it. But in the other case, you will take 15 minutes and everything is ready. Therefore, as long as time is being consumed in this experiment, as long as time is being consumed, it is being supplied in both cases, then it means for this water, which is great or which is large in amount, the bigger volume of water required greater heat or higher amount of heat or higher heat capacity for it to boil compared to the smaller one. And therefore, from this demonstration, then we can conclude that the quantity of heat required to raise a substance by a given unit of heat is directly proportional to the mass. Or, the greater the mass of a substance, then the higher the heat capacity. Substance. The higher the heat capacity. So at that note, we can define what heat capacity is. And the heat capacity is the amount of heat energy required to raise the temperature of a given mass of a substance by 1 unit, or by 1 degree Celsius, or capital C, or by 1 Kelvin, by 1 Kelvin. Therefore, you find now heat capacity abbreviated capital C is given by heat energy absorbed divided by temperature change. Heat energy absorbed. The heat energy can be capital Q, all over temperature change. We have abbreviated using the Greek letter theta, symbol for theta, to mean temperature change. Therefore, you find that now, for us to know the heat energy which is used to raise per unit, to raise the heat with a unit, either a degree Celsius, then we divide with the change in temperature, so that we know the heat which has been required for a single unit. And the heat required to raise a given mass is temperature by a single unit. Then it's what we call the heat capacity of the given substance. We can take an example on this. We can take an each on this. Let me write an example for that. The quantity of heat. We thought to calculate the quantity of heat energy. Calculate the quantity of heat energy required to raise the temperature of a metal block, to raise the temperature of a metal block with heat capacity of 460 joules per Kelvin from 15 degrees Celsius to 45 degrees Celsius, to 45 degrees Celsius, to 45 degrees Celsius. Let me have my calc, then we may go into the solution for this one now. Okay, we are taught to calculate. We have let me just mention this at that note before we continue very much, because the heat capacity is given by amount of heat absorbed all over the change in temperature. then we usually say that now the SI unit of heat capacity is joules per Kelvin, because we got the quantity of heat or the amount of heat which is in joules divided by change in temperature which is in Kelvin. Therefore, that's how we state. Now, remember that quantity of heat divided by the change in temperature gives us the heat capacity. And in this case, heat capacity, it's capital, I should make it capital, is equal to 460 joules per Kelvin. And also, the change in temperature will now be 45 minus from 15 to 45. Therefore, 15 to 45 we subtract the two and we get in 30. Therefore, the change in temperature here is 30. Change in temperature, initial and final. So final minus initial, we get the change in temperature. Therefore, now we can say now the heat capacity 460 is equal to the energy required to change by 30. This translates to Q being 460 by 30. This translates to 460 by 30, which is 13,800 joules. This is the energy. This is the energy required. The energy required. The answer is correct, but we like it more in figure when written in standard form. Times 10 raised to the power of 1, 2, 3, 4 joules. So you can just express it in standard form. It's not a sin to leave it at this level, but it is better when left in standard or expressed in standard form. So that's what you call the heat capacity. The heat capacity. I'd like us to define and elaborate another term called heat capacity. Heat capacity. Specific heat capacity, sorry. Specific heat capacity. Letter C now, small letter C, small letter C, small letter C. Therefore, we usually say that specific heat capacity is the heat energy required to change the temperature of a unit mass by 1 unit, or by 1, which is a specific unit now in this case, by 1 Kelvin. Therefore, under heat capacity, we say that it is the amount of heat energy required to change a given mass. But now, specific heat capacity is the amount of heat required to specifically now raise a mass of 1 kilogram, mass of 1 kilogram, so calling a unit mass, by 1 Kelvin. We call it specific heat capacity. This is what we mean, specific heat capacity. We're saying that now specific heat capacity will be the heat energy required to change by a single mass. Oh, let me clarify it, please. Let me clarify it. Let me clarify it. Now, because we said that heat capacity is the quantity of heat required to change a given mass by a single unit of temperature, then now we are saying specific is the amount of heat now required to specifically raise a single unit of mass by 1 Kelvin. And therefore we can say now heat capacity is now the quantity of heat divided by change in temperature, or else heat capacity is equals to, because Q over beta is heat capacity, this can translate to C is equal to the heat capacity but now per unit mass. The heat capacity but now per unit mass. Heat capacity but now per unit mass. Yeah. Heat capacity per unit mass. So we divide by mass. When we cross multiply, we can get that the mass times the specific heat capacity of the substance can give us the heat capacity. And we know that heat capacity is equal to the energy required over T. Therefore, we can have it here. So we can have mass times specific heat capacity will be equal to, instead of capital C, which is heat capacity, you can have Q. So again, this implies that, symbol means this implies that we cross multiply with this change in. So the quantity of heat absorbed can again be expressed by mass times specific heat capacity times change in temperature of a given substance. It's change in temperature of a given substance. Note, the SI unit of specific heat capacity is the joules per kilogram per Kelvin. Joules per kg per Kelvin. Because now it is specific heat capacity. I will now drop relevant examples now to relate the concepts, the heat capacity and the specific heat capacity, because we can see the two are related. They can be related, interrelated. We can manipulate the relationship to calculate different variables. This question for us: a block of metal of mass, 1.5 kilogram, which is suitably insulated, is heated from 30 degrees Celsius to 50 degrees Celsius in 8 minutes and 20 seconds by an electric heater rated 54 watts. It's capital W, 54 watts. Find part A, the quantity of heat supplied by the heater, the quantity of heat supplied heater. The quantity of heat supplied by the heater. B of it, the heat capacity of the block. The heat capacity of the block. The heat capacity of the block. And part C, its specific heat capacity. Its specific heat capacity. Its specific heat capacity. Its specific heat capacity. Therefore, that's the question. I'd like us now to solve it. To solve it together. Let me rub here. And I also get my calculator. So we are told that this is a metal block of mass 1.5 kilogram heated from 30 degrees Celsius to 50 degrees Celsius in 8 minutes and 20 seconds by a heater, and the heater is rated at 54 watts. Watts is the SI unit for power. Then find now the quantity of heat supplied by the era and the heat capacity of the block, then the specific heat capacity. So we can go straight to the solution of the question. Solution. Part A. Part A, we are given the power. We know that power is equals to the heat energy or the rate at which a machine converts energy per unit time. So the rate at which energy is changed per unit time, we call it power. This translates to that, then energy will be given by, the heat energy will be given by power times time. Therefore, the heat energy supplied by the heater will be power times time. Heat energy will be power, it's 54 watts, times time. And time should always deal with SI units. Therefore, 80 minutes by 60, so that they may become seconds. And once they become seconds now, we had 20. We had 20. So this should be 54 times, this is 480 plus 20. We get 500 seconds. So this 54 by 500. We get 27,000 joules. So this is the energy which is being supplied by the electric heater for that time, for 8 minutes and 20 seconds. We have 27,000 joules. Part B of the question. Part B of the question. The heat capacity of the block. Heat capacity of the block, capital C. We say that it is given by the energy which has been given. Okay, we could have called it Q anyway, but now when we were dealing with the topic called heating effects, we related heat energy using letter H. Heat energy. So this is energy generally, but this one is specifically heat energy. Therefore, the energy change in temperature. Therefore, the energy supplied in this case be 27,000 calculated in part B joules divided by change in temperature. Temperature is changing from 30 to 50. 50 to 30. And here we will get 27,000 divided by 20. Divided by 20. This will be 1350 joules per Kelvin. Joules per Kelvin. Joules per Kelvin. Let me focus the answer well. Yeah, like that. Joules per Kelvin. So that's how it's calculated. And lastly, part C. We thought that its specific heat capacity to be calculated. Specific heat capacity. C. You see that specific heat capacity now is heat capacity now per unit mass. Therefore, because we have heat capacity already calculated as 1350 and we have the mass as 1.5 kilogram, then we can get, divided by 1.5, we can get 900 joules per kilogram per Kelvin. Joules per kilogram per Kelvin. So that's how we get. Okay, alternatively, let's see whether this one will work. Alternatively, remember we said that the quantity of heat absorbed or generated, absorbed or released or lost, in other words, is given by mass times specific heat capacity times change in temperature. It's given by this formula, meaning that we can get the specific heat capacity as quantity of heat divided by mass times change in temperature. This will be specific, the energy supplied was this, divided by mass 1.5 times 27,000 divided by 1.5 by 20. This will give us 900 exactly. Joules per kilogram per Kelvin. Joules per kilogram per Kelvin. So that's how we get it. That's how we calculate it. The major concept in this topic, before we go into details, we've just calculated the specific heat capacity, the quantity of heat, the heat capacity itself. We will now be going to experiments which will show us how to determine specific heat capacity. But before then, I was saying that the specific concept, the main concept, the backbone of this topic is of heat and absorption of heat. Heat being lost, heat being gained. That is the baseline for this topic. Let me surrender several examples on the same. Several examples relating what I'm trying to argue here. The quantity of heat. The quantity of heat. Yes. Now a question is here. It says, is that a piece of copper, piece of copper of mass 60 grams and specific heat capacity and specific heat capacity of 390 goes from 90 to 40 degrees Celsius. Find the quantity of heat given out. Find the quantity of heat given out. Find the quantity of heat given out. So in this case, the quantity of heat given out. So now, the quantity of heat, we got mass here as 60 grams. Therefore, we can divide it by 1,000 to make it kilograms. There's a unit of mass. We also have specific heat capacity as 390 joules per kilogram per Kelvin is joules. And we also given a think change in temperature can be defined from 90 to 40, 50. So whenever temperature is changing, whether in Kelvin or in degrees Celsius, we don't convert to Kelvin. Whatever unit we get as the difference, we just use the absolute value in change in temperature. Therefore, in this case, we can now say that Q, which is the quantity of heat, is given by mass times specific capacity times change in temperature according to the formula we just stated. So everything is provided here. Mass times specific heat capacity times change in temperature. And this will give us our quantity of heat. This will give us the quantity of heat. So we will have 60 divided by 1,000. So instead of 10 power negative 3, we can have this 0, and this 0 cancelling. So we multiply 6 by 39 by 5. Yeah. So this is the quantity of heat which was released out when this metal of copper was cooling. So we can have a second example. Find the final temperature of water if a heater source rated 42 watts, it's 50 grams of water from 20 degrees Celsius to, okay, not to, in 5 minutes. In 5 minutes. Therefore, now, in this case now, we have to find the final temperature of water. If a heater rated 42 watts, it's 50 grams of water from 20 degrees Celsius in 5 minutes. There is something I was trying to mention, that in this topic, the concept is simply between two facts. Heat being lost by a certain body or a certain source and being absorbed at the same time by another. Though in this case, we are now going to assume that there is no heat lost to the environment. the heat supplied by the heater is 100% being absorbed into the water. I don't know whether we're together there. Because there is a heater supplying water and there is a heater supplying heat and a water absorbing the heat, we can say this, that the heat energy lost by heater, not lost, I think released or supplied. Yeah, supplied would be better one. The heat supplied by heater or by the heater, is equal to the heat absorbed by water, by the water, to be equal to the heat absorbed by the water. Now, we know that the heat is given by power times time now for the heater. Electric times time, which is the heat energy now. The energy, the heat energy supplied by heater will be given by power times time, which will be equal to the heat energy now for a body which is raised from a given temperature to another one with a known mass. Then we can say that the heat energy for the water it is going to absorb be mass times specific heat capacity times change in temperature, Therefore, we can now take power, which is 4 times time, which is 5 times 60 to make them seconds, will be equal to mass 50 times 10 raised to negative 3 to make them SI units kilogram, times specific capacity of water is 4200 times now the change in temperature, which we don't know. We don't know where the water has raised the temperature to. So in this case we shall have 42 by 5 by 60. This is giving us 600 of course joules. They are equal to, in this case now, we can have these 3 zeros being cancelled by negative 3 here. Therefore, we shall have 5 instead of 50 by 42 instead of 4200. 210 liter change in temperature. Therefore, we can get the change in temperature by dividing 12600 divided by 210. This is giving us 60. So now the temperature of water has varied by 60 degrees. So if the initial temperature is 20, it is being heated from 20 and it has risen because we are getting the change in temperature, not final temperature, the change in temperature. Therefore, final temperature now will be calculated when you take the 20, which is initial, plus the range at which temperature has varied from. So if this is a scale, water was being heated from 20 degrees Celsius, it has raised by 60 degrees Celsius, meaning that it has landed at 80. Therefore, final temperature of the water will be 60 plus 20, which is 80 degrees Celsius. So the final temperature for this water will be 80 degrees Celsius. In the next class, I'll be teaching the specific heat capacity of different substances, solids and liquids, using different methods. So thank you very much for following. Kindly subscribe to Shifting Grades. Share our link with your friends. God bless you.